Good morning, everyone. It's so nice to have you here. We are very excited for day 2 of CMU Energy Week 2022. We've been doing Energy Week since 2016 and are very, very excited about having you here in this virtual environment. Ordinarily, we'd be drinking coffee together, but very excited and hope you have a mug wherever you are. So we're going to start this morning with our student poster competition. I want to say a quick thank you to Alex Kramer. She just introduced herself, but ordinarily we have a number of staff who help us on this, but Alex took it on all by herself this year. So very thankful to Alex Kramer, who's one of our master's students in ESTMP at Carnegie Mellon. So I am Anna Siefken. I'm the Executive Director of the Wilton E. Scott Institute for Energy Innovation. If we have not linked in, please send me a connection. But more importantly, I want to make sure that you know how to reach the Scott Institute. So we have a newsletter that comes out once a month. We do regular programming like this throughout the year, in addition to Energy Week. But we also have incredible webinars and distinguished lectures that spotlight our faculty and thought leadership from around the world. So what is the Scott Institute? We are the research hub for energy and climate tech innovation at Carnegie Mellon. We're based in Pittsburgh, Pennsylvania, and we work with sponsored research, with faculty. We do partnerships of all kinds. We do a lot of programming. We support our students in our master's programs and undergrad, PhD, postdoc. But we also are very interested in entrepreneurship and innovation. And all of this is driving towards a sustainable, low carbon energy future for all of us. So I want to welcome our judges today. We have 6 esteemed judges, and I'm going to quickly go through their short bios. So our first judge is Kaimira Coney, who is a policy analyst researcher at the National Renewable Energy Laboratory, NREL, in the Accelerated Deployment and Decision Support Center. Her work focuses on equitable clean energy solutions in sustainable transportation and solar deployment. Welcome. Our second judge is Tim Lee, who is a CMU alum. He's part of the Walt Disney Company's corporate social responsibility and environmental, social, and governance work, where he focuses achieving the environmental goals of net zero greenhouse gas emissions and 100% zero carbon electricity. And his experiences include carbon accounting, renewable energy strategy, and public policy. Welcome, Tim. Next, we have another CMU alum, Purna Mujumdar, who is a power markets consultant at ICF, one of my former employers. Currently at ICF, she works with North American electricity markets, in the ISO, RTO, and regulated, especially ERCOT, where her work includes performing economic modeling, price forecasting, revenue assessment, and asset valuation for clients. Next, we have Stephen Euler, who is the VP of Compliance and Risk Management at Sea Power Energy Management. He brings a various background in the energy industry through experience at several companies, including General Electric, Eaton Corporation, and Westinghouse Electric Company. Next, Pamela Tomsky, who is the founder and director of the Research Experience in Carbon Sequestration, and she's passionate about clean energy solutions and is committed to empowering young professionals to be impactful. She's also been engaged with the U.S. Department of Energy's carbon capture, utilization, and storage program since 1998 in various external capacities. Last but not least, another CMU alum, Harry Levinson, who is the president and CEO of Skibo Energy, who's working on resilient, reliable, and safe clean energy storage. He brings decades of technical and management experience from working on large software projects for both government and industry customers, and he previously spent 15 years at CMU's Software Engineering Institute. So again, welcome to all 6 of our judges for today's poster competition. We are so glad to have you here with us. And now I'm going to pass it back to you, Alex.
Thank you. And thank you again to all our judges for being here today. So really quick, just going over the rules. Each team has 5 minutes to present. I will announce the start and I will have a timer going, so exactly 5 minutes. A timer will go off from my end, or I will also say time. At the audience and judges will have opportunities at the end to ask questions in breakout rooms, so there'll be no questions directly after. And keep your mic muted and video off unless you're presenting. Next slide. The team order is here, but in the chat, I just put a document that you should all have access to. It has the agenda for today, this schedule right here, and the full bios of the judges. There are also 2 teams that are video presentations and 1 team that is rescinded. So there will actually only be 16 teams presenting, but there are the links to the videos if you'd like to watch those after. Next slide. And then just updating the prizes for everybody. There was no full undergraduate teams and there was only 1 undergraduate that submitted. So we have redistributed the undergraduate prize to the other prizes. So these are the new prize values. There will be first, second, and third and overall, and then the judges will select the idea that they think is the most innovative research idea. So with that being said, Navishka, you are the first presenter. So we'll allow you to share your screen, and when you're ready, let's begin our presentations.
Are you able to see my screen?
Kristen, I think you have to stop sharing your screen. All right, there you go. We can see your screen.
Yes, perfect. Good morning. So today I'm going to be sharing my research on the solar energy potential to reduce inequality in vulnerable communities in Pittsburgh. I've worked on this project under the guidance of Dr. Konstantin Samaras and Dr. Destiny Knock. So one of the first things we have to start by addressing when we look at this topic is the history and legacy of redlining in most of the major cities in the United States. And Pittsburgh is one of those. So the first question that would naturally come to mind is, well, what is redlining for somebody who doesn't understand or doesn't know of the term? So redlining is the historic practice of denying or allotting home loans based on where an applicant lives. So this allowed home ownership and to be predominantly focused in communities of white communities and marginalized communities of color. And so this is something that then went on to lead to a variety of issues. And these communities also currently faced the highest lead exposure, are the communities that suffer from the highest energy burdens. And my research is looking to see how renewable energy in these areas could provide a solution to lower the energy burden for these communities. In order to do that, I evaluated and first compiled a data set of the 100 largest cities in Pittsburgh. So I did this by incorporating data on the solar potential in these cities, on the current energy mix, on the current electricity costs and the poverty line and all of these individual cities. I looked at a variety of factors that influence all of this and compiled all of this into a large data set. I then conducted a specific deep dive into Pittsburgh and analyzed the census tracts in Pittsburgh specifically to look at the social demographics and the redlined areas. I used GIS to be able to do this, and I mapped and assessed the potential for renewable energy. So I exported the data for Pittsburgh onto GIS to be able to visualize it. As we can see in my results section, in figure 1, we have the Homeowners Loan Corporation, where the red and yellow districts are where redlining has occurred. And when we go down to figure 3, we can see the solar potential in Pittsburgh with the darker color representing the areas with the highest potential. In figure 5, I overlaid the solar energy potential and the redlining to be able to see the solar potential and map out how much solar potential these districts have. And it's remarkable to see that the annual solar potential in these areas comes to around 2,635 gigawatts per year, which is a significant amount of energy that can be harnessed to help alleviate the energy burden in these communities. It's also remarkable and starking to see the lead exposure score in these red line districts. So I used a tool developed by the Department of Health to run a code to be able to give me the data for Pittsburgh. And we were able to see that some areas have the highest lead exposure score of 10. It's another interesting thing is that the highest lead exposure score possible in the United States is 10. And a lot of the red line communities in Pittsburgh today, quantitatively 57% have a lead exposure score of 10. This is something that definitely needs to be looked into and worked upon, and being able to harness solar energy potential to be able to do that is a step in the right direction. And this is what my research focused on with a deep dive to Pittsburgh. Thank you so much.
Great work, Navishka. All right, next we have Catherine Jordan.
All right. All right, are you able to see my screen?
Yes.
Great. All right, my name is Katie Jordan. I'm a third-year PhD student in the Department of Engineering and Public Policy, and I work with doctors Paulina Jaramillo, Nick Muller, and Peter Adams. So between the years of 1990 and 2018, greenhouse gas emissions in the US transportation sector rose nearly 25%. In order to address this, federal, state, and corporate stakeholders are shifting from gas and diesel vehicles to zero-emission vehicles, including electric vehicles and hydrogen fuel cell vehicles. Unfortunately, without more comprehensive climate policy to reduce electric sector emissions, these so-called zero-emission vehicles are not really zero-emission. In my work, I explore how we can achieve deep reductions in economy-wide emissions by combining policy instruments in transportation and electric sectors. To do this, I use TMOA, the Tools for Energy Model Optimization and Analysis. The inputs for this model are capital, fixed, and variable costs, technology efficiency, and emissions activity. The model performs a linear least cost optimization, and the outputs include technology deployment, energy consumption, greenhouse gas and local air pollutant emissions, as well as system costs. I model a number of standalone policy instruments, including zero-emission vehicle standards on both light-duty vehicles, as well as all on-road vehicles, which includes cars, trucks, and buses. I also look at a clean electricity standard and an economy-wide carbon tax. But a key part of my work is modeling interactions between multiple policies. For example, a light-duty zero-emission vehicle standard and a clean electricity standard. So diving a little bit into my results, all of these plots I'm about to show you show transport and electric CO2 emissions over time under various scenarios that I modeled. The left graph shows a fairly intuitive conclusion that when designing zero-emission vehicle standards, if we include medium and heavy-duty vehicles, we increase abatement potential. The graph on the right shows in the red line a clean electricity standard on its own, and we see that there are steep emissions declines from 2030 to 2040, but without policies that encourage additional electrification, emissions reductions level off by 2040. So you can compare it to a clean electricity standard with a light-duty zero-emission vehicle standard, the blue line there. Next, I'm going to compare a light-duty zero-emission vehicle standard with a carbon tax, which is this gray line with the triangles, to this lime green line, which shows an all on-road zero-emission vehicle standard and a clean electricity standard. We find that those policies lead to similar cumulative emissions reductions, but due to the high cost of decarbonizing the transportation sector, emissions reductions in the last few time periods, 2045 and 2050, are actually greater under the clean electricity standard, which may indicate diminishing benefits from a carbon tax. Under a standalone zero-emission vehicle standard, natural gas generation increases to meet elevated electricity demand. So the key thing from this figure, we're showing primary energy demand in 2050. The business as usual, natural gas generation is this red bar, And if we look at the two zero emission vehicle standard scenarios without climate policy, that red bar has grown. And clearly natural gas generation, additional natural gas generation is antithetical to deep decarbonization goals. We also know that zero emission vehicles will have large impacts on infrastructure. Using charger capacities from NREL, we estimate that nearly 13 million level 2 and about 600,000 DC fast chargers could be required just to serve the electrified light duty vehicles under our modeled policies. Overall, we find that a carbon tax and a zero emission vehicle standard has the lowest cumulative emissions, but reductions plateau in later years, indicating that there may be diminishing benefits from the tax. We also find that a clean electricity standard complements electrification standards in the transportation sector. We recommend that if a zero emission standard is implemented, that all on-road vehicles are included, and policymakers could implement additional policies in other sectors of the economy to achieve even greater emissions reductions. For example, minimum electrification standards in the commercial and residential building sectors. Thank you.
Thank you so much, Katie. The next presentation is Aaron, Chris, Raul, and Lucas.
Yeah, good morning, everybody. Yeah, just to kick it off, me and my team members looked into what basically the implications were for several scenarios for heavy electric truck adoption in the United States. Just to kind of reinforce the background for this, trucking in the United States is a pretty substantial portion of energy consumption in comparison to rail or water shipping. And so overall, our objectives were basically to look at what the implications were out to about 2030 for diesel consumption, electricity consumption, and potential impacts and needs for vehicle charging. Our assumptions for the project were effectively two scenarios. One was based on a particular analysis that estimated a roughly a 50% growth rate per year for heavy electric trucks. But then also we utilized a much more optimistic, we'll say, scenario of 80% BEV truck sales by 2030, and then kind of back propagated the growth from that. And then one kind of look at that, how that would affect consumption. Effectively, if you really want to take a look at overall diesel consumption in the future, we basically calculated a standard expected confidence interval for diesel consumption. So this is basically treating diesel consumption as though electrification wasn't happening at all. We would still expect some kind of bounds on diesel consumption for various factors, economic performance, things like that. And we wanted to look at how much the heavy electric trucks would change this. To understand kind of the impacts, though, one of the things that's really quite important is understanding mission range of trucks. Effectively, and this is kind of pulled from Department of Transportation information, most heavy trucking, in fact, operates extremely close to home, 50 miles or less, as you can see in the pie chart. And this has really substantial impacts in terms of what kind of electric charging we believe is going to be needed in the future. So I'll go ahead and turn it over to Chris for.
Okay, so to continue with Lucas's analysis, we start by calculating the avoided amount of diesel consumption, and we do that by estimating the total number of BEV trucks in 2022 to 2030. Then using the total number of miles and miles per gallon, we can estimate like how much total diesel that will be saved by doing this transaction. And secondly, after that, we can then use a conversion to convert these diesel saved into electricity that would be needed. So that is plotted in the results that we will go to later. And thirdly, in our objectives, we will be introducing carbon intensity for both diesel combustion and also US grid electricity to have an estimation of how much CO2 emission that would be reduced. So As you can see in the table, we have two different carbon intensity. The first, with diesel combustion, we estimate that it will be more of a constant because it is more of a mature technology. As for US grid electricity, there would be a significant reduced when we count the increase in renewable energy mix into the electricity grid. As for the results, you can see that for US electricity consumption impact, there would be a very significant change. And we want you to focus more on the orange, which is the high scenario with a 19% market share. You can see that in 2030, there would be increase about 2% to 2.5% of total generation that would be needed, projecting to 100% market share, which would yield about 10% more electricity that would be needed for electrification. And for net CO2 emissions reduced, there is a three times less of a difference in comparison for the two scenarios, which is significant. And moving on to discussions, we have 4 points. The first point is that expected growth rate of electric trucks will have a marginal impact. So policy recommendations would be advised to push forward with the transition. And for incentivizing the transition, we want to focus more on installing overnight charging because of mission range percentages of the trucks. And thirdly, achieving 100% market shares in 2030 will require about 10% increase in electricity consumption. So to plan in the future, we should start planning on upgrading an electric grid right now. And lastly, for city transit bus to take up less than 2% of all class 7 and 8 trucks registered in 2018, the impact of electrification for those trucks might be limited. However, we must state that further analysis would be needed because these trucks might have a longer mileage in total. So yeah, this is our presentation. Thank you so much for your attention.
Thank you so much, team. Next we have Xiao Shen.
Okay, let me try to share my screen. Can you see my screen now?
Yes, we can see it.
Okay, great. Okay, so hello everyone, I'm Xiao Chen Sun, and I'm a PhD student in public policy for Heinz, and thanks for having me here today. And the poster I presented today is based on joint work with my advisors Karen Clay and Edson Savernini. So the air quality monitors have been central to measuring and later regulating the air pollution in the United States. The US EPA has implemented a series of environmental policies starting in the 1970s, and many of them are complied based on the EPA monitors reading. However, these EPA monitors are sparsely located in the United States, and not every monitor report data every month or year. So the introduction of the satellite-based measures of the air pollution serves as a good addition to the EPA monitor data to fill the measurement gap for policy evaluation. But the high resolution and the large coverage of the satellite data actually comes with a cost of prediction accuracy. So in this poster, we examine the impact of the Exit Rain program, which is a cap and trade program that regulates SO2 emission on local air pollution, leveraging the NASA satellite data and compare it to the impact estimated using the EPA monitoring data. So the goal is to try to see whether there is a difference in policy impact estimates between monitoring and satellite data, and second, if there's a difference, then why. So we use the difference in differences models in econometrics to estimate a policy impact. So the figure here shows the locations of the data points from the different data sets. So the AQS unbalanced panel refers to the all EPA monitors. So we see that most of them are located in the eastern coast of the United States. And also note that not every location here reports data every month or every year. And some locations only reports data in certain months, and then the monitors are removed in later time. So when restricting the monitors to the ones that report data uninterruptedly between the study period, we see here very few monitor sites left in the northeastern of the United States. On the other hand, however, if we look at the NASA satellite data set, they cover the entire United States uninterruptedly during the study period. So despite the difference in resolutions between the monitor data and the satellite data, the readings are actually highly correlated as presented in this table. So the R square here is quite large, which means that 60% of the variation in monitoring data can actually be predicted using the satellite data. So given the highly correlated data points between the monitoring data and the satellite data, the discussion of the policy estimates actually show a different story. So if we estimate the impact of the XRIM program with data points from the EPA monitor data and the NASA satellite data in months when EPA monitors are actually active, the results are reported in columns 1 and 2. So the coefficient estimates here are both negative, meaning that there is a significant negative effect from the XRIM program on the local SO2 concentrations. The consistent estimates between the monitor data and the NASA satellite data here suggested that the potential prediction error associated with the satellite data does not affect the direction of the estimated policy impact. So interestingly, after we include the satellite data in months when the EPA monitor data are not available, which are the results reported in columns 3 and 4 here, the coefficients of the XRIM program indicator switch sign to positive. This means that the SO2 concentration reduction in XRIM program facility location is actually in fact slower relative to the control group locations. So given the contradictory results between these two, the first two columns and the last two columns, we create this scatter plot for comparison. The vertical axis corresponds to the data set we used in column 2, which is the NASA satellite data in months when the EPA monitors are in place. And then the horizontal axis corresponds to data we used in column 3, which is the NASA satellite data after we include additional months when EPA monitors are not in place. So if the dots lay on the diagonal of this plot, the two measurements align with each other. But as observed, many of the dots lay on the right bottom of this figure, which is suggested that the average concentration in EPA monitor active months is always lower than the average measurements when EPA monitors are not available. So in other words, months with a higher concentration might be the months when the EPA monitor readings were not available. So with that, we argue that the policy impact estimates can be severely biased and misleading, even if the difference between the monitor and the satellite data are minimal, and attention should be paid when pollution concentration is not captured by the EPA monitors. And thank you, and happy to take your questions you might have.
Awesome, thank you so much. We're gonna be taking questions at the end, and that was a wonderful presentation. So I'm sure there will be follow-up. The next presenter is Naeem.
All right, thank you so much. All right, everybody can see my screen, I hope.
Yes, we can see it.
Excellent, excellent. So good morning, everyone. And again, thanks for the judges and fellow competitors. Indeed, very exciting presentation so far. So today I'm going to be presenting my research, part of my Doctor of Design and Architecture Studies at Carnegie Mellon, titled Design Optimization for Net Zero Energy Apartment Buildings in Lebanon. And this research has been done under the guidance of Dr. Erica Cochran-Hameen. And I gratefully thank her for all her support. So to start off, Lebanon has been deeply impacted by climate change and its various impacts. And as we speak today, the country is actually going through three crises: an economic, financial, and social one. And they've severely impacted all sectors of the population. And furthermore, energy consumption in Lebanon has seen a drastic increase over the past decades, totaling about 4% per year compared to the baseline. And to that end, Lebanon's residential energy sector consumes 30 to 45% of the total energy consumption, compared to only 25% in regional Mediterranean countries. And most of the energy in Lebanon is generated via fossil fuels imported from countries in the Gulf and regional counterparts. My research have shown that a prominent solution to these problems of energy consumption and rising electricity prices, which have been drastic over the last year, is adopting zero energy housing as a new construction design paradigm. This approach can offer households resiliency, independence, and autonomy. And more importantly, it will provide Lebanese households with a robust path towards achieving environmental justice, social equity, and economic stability. Unfortunately, net zero energy buildings has not been widely adopted in Lebanon for three primary reasons: financial, informational, and behavioral reasons. So in my research, I adopted the following methodology, encompassing three main steps. First, I conducted perception surveys encompassing 1,200 respondents. Second, I employed an iterative parametric energy modeling and simulation approach. And third, I developed comprehensive net zero energy guidelines and frameworks. The main objective of this study, the fundamental premise, is really to provide Lebanese people a viable path towards eliminating energy poverty, providing social equity, and reducing financial strain. And I plan to achieve this by developing alternative solutions to residential building practices, developing a robust framework for net zero energy practices in Lebanon, raising public awareness on energy use and conservation, and achieving resiliency, independence, and safety. My simulation results have shown that net zero energy buildings indeed are a viable approach in Lebanon's residential market, and therefore could be applicable to the regional and counterparts in the Mediterranean. And collectively, building design and system optimization upgrades yielded a 56% reduction in energy compared to the baseline. And when we add photovoltaic integration towards net zero energy optimization, the research yielded a 100% reduction in energy consumption and CO2 emissions, as well as life cycle operating carbon use intensity. The research delivered three primary deliverables. First, a set of net zero energy guidelines encompassing passive and active strategies, and also encompassing existing retrofits for buildings in Lebanon. And the deliverable guidelines are tailored to homeowners, developers, architects, and various stakeholders. The second main deliverable is an informational mobile app designed to disseminate the information and educate people about net zero energy practices. And then third deliverable is an informational website that also acts as a platform to inform stakeholders and provide them with online calculators to actually customize their own zero energy approaches. In conclusion, zero energy buildings provide a viable alternative to traditional residential construction practices. They reduce energy consumption and utility costs. They provide economic independence, social equity, safety, and resiliency. Most importantly, they eliminate energy poverty in a country that is stricken by economic impacts. And collectively, they reduce environmental degradation. The contribution of the study is really critical and really paramount because it has a severe impact on households in Lebanon. It's my hope that this bottom-up approach will generate a revolution, a paradigm shift in the normal construction practices, not only in Lebanon, but in the entire region. Thank you very much.
Thank you so much. And I'm not a judge, but those are great colors on your poster. The next poster is Manish, Pratit, Shruti, and Ritika.
Hello, everyone. I hope you can see my screen.
Yes, we can see it.
Cool. So, hello, everyone. My name is Manish, and I am a master's student in Energy, Science, Technology, and Policy here at Carnegie Mellon. The title of our poster is Energy Demand in Paper and Pulp Industry. And my group members are myself, Pratit Dave, Ritika Chopra, and Shruti Ishwar. So let's get started. The objective of our poster is to evaluate the energy consumption in the paper and pulp industry and how we can reduce it by adopting a twofold approach. One is replacing all the current equipment, technologies, and processes with their most energy efficient alternatives that are available somewhere in the world and evaluating how much energy is consumed for producing virgin paper and compare it with the energy required to produce recycled paper. So why are we focusing on paper and pulp industry? It's because 11% of the total energy consumed by the manufacturing sector in US goes into the paper and pulp industry. This image shows the entire process of producing paper. So in 2010, from 2010 to 2019, we've seen a more than $15 billion increase in the market worth of the industry. However, the production of paper has gone down and the energy consumed in trillion BTU has gone down as well. The reasons for this we'll be discussing later on in the poster, but one of the main reasons is that there's a reduction in the demand of paper itself because of replacement by electronics like iPads and mobile phones. So in our quantitative analysis, we take a look at the energy consumed by virgin paper, which is 33 million BTU per ton, and by recycled paper, which is 22 million BTUs per ton. This you can see there's a difference of 11 million BTUs per ton when we replace virgin paper by recycled paper. In this graph here, we can see that the total energy consumption by the industry has gone down from 2000 to 2018. The reason that we can see here is that this orange part, which is the energy consumed by the recycled paper, is going up. The percentage is going up and the energy consumed by virgin paper comes down, right? So this leads to a total energy decrease, which means that recycled paper take up less energy, which is also shown by this yellow line. This is the energy intensity, which has also gone down over the years. Now, why has recycled paper increased over the years? It's because, as we can see now, there are separate dustbins wherein you can throw your waste paper and they can go into recycling. There have been improvements in waste collection and transportation technologies, and hence more waste paper is coming into factories, which can then get recycled. In this image, we are comparing the energy consumption of every process in the industry in 2010 and 2019. Energy consumed by each process has gone down, and but the one factor that remains is that the two most energy intense processes remain the same. The most energy goes into powerhouse losses and the second most goes into paper drying, and these two put together take up 50% of the total energy consumption. Now in figure 5, what we're doing is we're comparing the energy consumption that is currently going on in the United States with the current machinery, equipment, and technologies. And we're comparing it to this orange part, which is the state-of-the-art version of those processes, technologies, and equipments. Now, what is state-of-the-art? It is the most energy efficient process or equipment available and being used in an industry somewhere in the world. And we are assuming here that it is financially viable to do the same in the United States. And so we're comparing the energy consumption of the current technologies with the state of the art. And we can see there is a reduction in energy consumption in all processes, and also the total energy consumption comes down. So finally, in our results, we tried to show the energy savings potential of each process individually. Like, what if we just make one process energy efficient? How much would that thing save energy for us, right? And as we can see, the two most energy intense processes are the ones which have the highest energy savings potential. And just by making these two processes energy efficient, we can save 189 trillion BTU, which is a huge amount of energy. Here in our sensitivity analysis, we've analyzed what if we increase the percentage of recycled paper further. So in 2019, the percentage was 65%. So what if we go up to 100%? That is, all the paper that we manufacture is recycled paper. By only doing this, we'll be saving 15% of total energy that is consumed by the industry. So finally, in our recommendations, we recommend two things. First, because if we just focus on the two most energy intense processes and make them energy efficient by improving boiler efficiency, improving steam distribution, improving combined heat and power systems, and using advanced dryer control, we can, just by doing this, we can save 50% of the total possible energy savings. Also, if we increase the production percentage of recycled paper through further improving waste paper collection and transportation technologies, we'll be further saving our energy for this sector. That's it from my side. Thank you so much for your attention.
Thank you, Manish. That was great. Next presentation is Juan.
Hi, everyone. Let me just share screen. Can everyone see the screen?
Yes.
Let me just minimize this. One second. Okay. So yes, hi everyone. My name is Juan Mesa. I'm in Sean Lister's group. I'm in the Department of Mechanical Engineering. I'm a PhD student there, and my research is focused on the durability of a new ionomer in fuel cells. And I want to go into the process of this ionomer, what it basically does. The ionomer in a fuel cell is used in two specific places. It's used as a proton exchange membrane that separates the cathode from the anode. And so it allows for the proton conduction between the electrodes, as well as in the catalyst layer. It's used to bind the platinum and carbon particles together. And so it serves two different purposes. So traditionally, what's always been used is Nafion PFSA polymer, which is a perfluorosulfonic acid. And the status quo has always been Nafion. It's been used for several years and has been a great ionomer. In recent years, however, a new chemistry came out, and it's called HOPI. And we did this in conjunction with Chemours and Ballard, Chemours being the ones that produced HOPI. And it's been revolutionary so far. It's proven great results in terms of what it does, which is exactly its name. It's a high oxygen permeability ionomer. So it has shown increased oxygen transport rates in order to improve the efficiency of the fuel cell. And it has enhanced oxygen reduction reaction activity. And this is due to the mitigation of catalyst poisoning by sulfonate anion groups. So it's shown great results. The problem, however, is that we don't know much regarding its degradation. We know about Nafion and how it degrades much more, but we don't know much about HOPI just because it's so new. And so our objective in our lab was to really get to know this new ionomer, explore its degradation, and be able to evaluate the chemical stability, promote, of course, the degradation, and determine the reasons as to why it degrades, and just ask all of those questions. And as you can see here, in the objective area, there's a picture of a fresh membrane electrode assembly. And then there's one here of a degraded one. So we want to apply a similar process, but we want to do it specifically for the catalyst ionomer. And basically our approach is we created, so on the day one, we created the membrane electrode assembly. We created the ink in-house, the electrodes. We compiled it all together, made the fuel cell, placed it in the bipolar plate, and then hooked it up to the fuel cell test stand and the potentiostat for characterization. And so in day one, we did a break-in process. We broke it in, we warmed it up, kind of greased the gears a bit, and got it to the level where we wanted it to be. And then after that, we did a voltage recovery to get the voltage back up to its normal state, or even better sometimes. And so this was what we did in day one. And then from days 2 through day 5, we did a beginning of life test analysis. So these are the limiting current, electrochemical and spectroscopy, cyclic voltammetry, and IV potential curves. So we did this, and then we did an accelerated stress test. The Department of Energy has a protocol, which is an open circuit voltage for long periods of time. So we ran the DOE protocol, and we did it for 7 hours from days 2 through day 5. And then we did an end of life analysis afterwards. And so with all of this data, we compiled it together. We ran some data analysis, and we got the plots that you can see here. And so there was some chemical, and so from the results that we gathered, there was some chemical degradation in terms of the oxygen transport resistance. It did increase a bit, but nothing that we would expect from, not an extraordinary result that is uncommon for fuel cells. And so what we noticed is that HOPI really performed better than we expected. And as you can see as well from the plots, there wasn't much of a shift in the beginning of life and the end of life, as well as with the transport, pressure dependent transport resistance, there wasn't much of a shift. And so what we determined is that this suggests that HOPI can be used for heavy duty fuel cell vehicles that need greater than 25,000 hour lifetimes. And we believe this is good for now, but for future work, we expect to do longer OCV ASTs to promote that chemical degradation, because that's what we really want to do. We want to promote that chemical degradation. And we also want to visualize it as well. So by performing some visual characterization, we'd like to do that. and apply novel AST techniques, something like the Fenton's test, which is also a chemical degradation accelerated stress test. And of course, compare it to benchmark Nafion D2020. So yes, thank you everyone. And I hope you like the presentation.
Thank you so much.
Sure. Yep.
Great. Yeah, the next presenter is Zakar.
Well, can everyone hear me?
Yes, and we can see your presentation.
Great. All right, so my name is Zakar White. I'll be presenting on multi-scale modeling of oxygen reduction reaction for a polymer electrolyte membrane fuel cell, a PEM fuel cell. I guess from a higher view, electric current is generated in a PEM fuel cell when oxygen combines with electrons and protons. In what we call the oxygen reduction reaction is combined in the catalyst layer. And we use modeling to try and explain some of the transport phenomena, as well as trying to optimize some of the electrode structure in order to improve efficiency, durability, as well as power density. State-of-the-art catalysts use high surface area carbon black coated with a polymer to aid in the proton transport. This was first seen in 2005 by a sun model where we have like a spherical pellet coated with a film. But in recent works, it has been shown that the film actually blocks some of the catalyst sites and it reduces the electrocatalytic activity. This was shown in Ramaswamy's model in 2020, trying to decouple the two phenomena. My work focuses on trying to couple the two phenomena of the oxygen transport and through the film, the flux through the film, as well as the reactions inside of the catalyst. We see that by comparing it against the uncoupled model, our coupled model creates about a 10% reduction in current. So the other model overestimates the amount of current that is being generated. We then plug this into a linear regression model to try and estimate what it does on a larger scale. So we run a parametric study. We find a polynomial that matches the current or estimates the amount of current that a single agglomerate can generate, and we plug that inside of a full fuel cell stack. Inside this fuel cell stack, we generate a polynomial based on a single agglomerate. It generates a current, and we can use that as a source or sink term inside of a stack. And we go into the next cell and we do the entire process again. We find that it has a really good match to our experimental data. And yeah, we have a really good match to our experimental data. I think, yeah, that's the end of my presentation.
Awesome, thank you so much. So we are about at halfway, and so I just want to see, the judges can either put kind of a thumbs up or speak out if you'd like a 5-minute break to catch up, or we can continue on to the next presentation. So I'll just give it a moment for any judges to message me or ask for a break if they need. Okay, it seems like we are probably good to continue on. So the next presenter, let me see what that was really quick, is Philip.
Hi. I hope you're able to hear and see me.
Yes, we can hear you and see your presentation.
Thanks, Alexandra. All right. Hi, all. My name is Philippe Schicker, and I am presenting my research on the design and feasibility study of biomass-driven combined heat and power systems for rural communities. As an introduction, I conducted a case study to demonstrate biomass-driven combined heat and power system, or BCHP, applications in rural communities to identify the feasibility of biomass as a fuel type, grid independence opportunities, as well as climate justice implications. The CHP system is made of a power generation unit, or PGU, as well as a boiler, where the PGU is fueled using wood pellets, in this case, producing electricity and waste heat that is captured to meet the energy needs of buildings or communities. If the system is designed properly, it can operate independently from the energy grid, which is a great advantage in rural communities, especially after natural disasters. Based on size parameters, Ackerman, Mississippi was selected, and through the use of Google Maps and Department of Energy software Energy Plus, I modeled the energy consumption of the buildings and identified their overall energy footprint. I compiled the BCHP system data and compared it against a reference system, which is natural gas powered, to determine primary energy consumption, operational cost, carbon dioxide emission saving, as well as system payback period. In addition, determining a threshold is particularly important for this application. So a PGU is usually sized based on the electric output. So a 600 kilowatt hour PGU produces 600 kilowatt hours of electric output. However, it produces about double the thermal output. So a 50% threshold system is contingent on the thermal output value. So for a 600 kilowatt hour system with 1200 kilowatt hours of thermal energy output, a 50% threshold value would represent 600 kilowatt hours of thermal energy output. And this is really important when comparing winter and summer days, especially on the climate region. For example, during summer days in warmer climate region, there's very low thermal need. In the winter, however, the thermal demand is much higher. And so once the threshold value is exceeded of the system turns on and provides both electricity and thermal energy. When comparing different PGU sizes, the parametric analysis showed that a 600 kilowatt hour system provides the greatest savings. And you can see this in the center table. This is displayed in total numbers, as well as percentage-wise in the graph on the bottom center. A major factor on the overall costs is the initial price for wood pellets, which was used as the biofuel. Varying the price and highlighting the cost changes at two different threshold systems, it becomes very clear that at $200 per ton, it's very unfeasible to run this system since it creates operational losses. You can see that at the table in the top left on the right side. Moving on to the payback period analysis, varying the PGU size and the threshold values, it becomes very evident that feasible payback periods only exists for systems up to 600 kilowatt hours, or at a lower threshold value, up to 1200 kilowatt hour systems. And this depends mainly on stakeholders. The graph on the right side displays the varying payback periods of a 600 kilowatt hour system, the one we identified to be ideal, for differentiating wood pellet price points, ranging from $50 a ton to $150 a ton. The primary conclusion of this research is that wood pellets can serve as a viable alternative fuel source for BCHP systems. This is great news, especially through the greenhouse gas emissions that are connected with natural gas. Furthermore, a threshold value may be necessary depending on the system configuration, but more importantly on the climate zone as well. Hotter climate zones may benefit from a higher threshold value. In the future, the price of wood pellets should be reduced to increase the viability of the system, and this provides really great opportunity for policymakers to create incentive policies. And lastly, most importantly, the adjustments to biomass-driven combined heating, cooling, and power systems will increase the effectiveness of these systems, even in warm climate zones where the thermal demand may not be as large, but the cooling demand may be. I appreciate your time, and I welcome questions in the breakout rooms. Thank you.
Thank you so much, Philippe. That was great. Our next presentation is Sean.
Well, thanks a lot. My name's Sean Smiley. I'm a PhD student in the Department of Engineering and Public Policy here at Carnegie Mellon, and I'm here to convince you that greenhouse gas estimates of LNG exports must include global market effects. If you're interested in the project, there's a link to the paper up in the top left here. So for those of you who aren't aware, we are in the middle of a LNG export terminal construction boom here. Considering both US and Canada, we went from having almost zero export capacity just a few years ago to now being able to export about 11% of our of what I'm calling domestic production here for US and Canada. And just counting what's already under construction, we'll be able to export about 27% of current production. So that, as many of you probably know, has led to a lot of interest in what is the climate impact of some of these export terminals. So traditionally, the way that's been done is through attributional life cycle analysis, LCA. That's considering the direct emissions across the whole life cycle, meaning producing, exporting, combusting the natural gas. And to determine whether or not what the climate impact of this is, what they do is they take the LCA values for LNG and they take the difference from the LCA values of another fuel source. Usually that's coal. If the coal emissions are higher than the LNG emissions, then we say, well, exports are good because the difference means that GHG emissions would go down. What that does is it's implicitly assuming that there's perfect substitution between LNG and coal, and that ignores some of the market changes that happen because of these export terminals. They are going to change energy prices, both domestically and internationally, and that will lead to changes in the in quantities of both coal and natural gas. So the research question here is, how do GHG assessments of LNG export terminals change if actual LNG coal substitution rates and rebound effects on international natural gas consumption are considered? I'm just on the method, all I'm going to say here is I am considering a 2.1 billion cubic feet per day LNG export project. And I'm combining the prior LCA studies with an economic model. So on the right here, this is my main results. The x-axis has GHG emissions, and the curves represent the uncertainty in the estimate. On the right here, the yellow curve is saying that the LCA emissions from a LNG terminal this size is something like 60 megatons of CO2 equivalent. And if you take that value and you minus out what the coal life cycle emissions are for an equivalent amount of energy needed to satisfy the same energy demand, for electricity, you get the purple curve, and for heat, you get the blue curve. And because those are basically all on the negative side, you would say almost certainly, considering the uncertainty here, you would have a reduction in CO2 emissions. Now the green curve here is, so that's the blue and the purple curve, that's the traditional method. The green curve is my study where I'm using the same LCA values, but I'm now just combining it with an economic model. And you can see that it's predicting a much smaller climate benefit. At the median here, at the 50th percentile, the benefit compared to the electricity curve is about 80% smaller. And there's about a 25% chance that emissions might actually go up. Why is that? It's like I said, energy prices are changing. So because gas prices domestically will go up with these export terminals, we're now going to use more coal than we would if there were no export terminals. Because it will lower the price of gas and by extension coal abroad, we're going to use more energy in total internationally. So we're burning more fuels and more of the fossil fuels in total, and that will lead to a rise in emissions. So just to conclude, ignoring the market effects of LNG export terminals, as has been done traditionally, overstates their climate benefit. And LNG project regulators should be requiring consideration of these substitution and rebound effects in their GHG assessments of LNG terminals. Thank you very much.
Thank you, Sean, and feel free to put in the chat the link you mentioned at the beginning for anyone more interested in your work. The next presenter is Zan. Hi, Zan, I think you're muted.
Hello, everyone. My name is Zhan Shi. I'm a first-year PhD student in the Building Performance and Diagnostic program, and my topic is the application of hempcrete materials in the architecture field. And my research is directed by the Professor Erica and Professor Jeremy. According to the United Nations Environment and International Energy Agency, 39% of the total global carbon emission and energy consumption is in building construction. From the life cycle perspective, hempcrete is a promising sustainable material, has negative energy consumption. It is also an effective carbon sink, which can greatly reduce the building construction embodied energy. In the scenarios of hempcrete researches below, hempcrete is discussed from the block skills to the spatial skills. Those experiments give the most effective ways of how the solar chimney combines with the hempcrete building envelope topologies. And in the first phase of the researches, we discuss about how does the life cycle assessment of the hempcrete in the ecology perspective and the energy perspective, which includes the how does these materials grow up and how does these materials to be recycled, and how does the energy flows goes. And then in the second phase of the researches, first of all, we are going to discuss about the combination of the sustainable materials hempcrete with the typical passive strategy, solar chimney. First of all, we discuss the geometry of the solar chimney. And here is the ventilation simulation diagram. We can find the different iteration of the height of the solar chimney in certain scales of the space, from 15 feet to 20 feet. This pattern will change to bounce off the ground in the 20 feet height of the chimney. So this will create a better vent pattern. Then we discuss the section geometry of this solar chimney. And we can say when the solar chimney section will be the semicircle ones, the wind pattern will have a circular path. So this will create a more comfortable indoor ventilation. And then we did a 3D printing physical experiment to double check the result of the computational simulation. And this diagram shows the component of our experiment. We evaluate the performance of the space with the cooling speed of the hot water, and we get the same result of as the simulation results. And then we discussed the block skills of the solar chimney bricks. Here we found the denser block and the block with the convex surface pattern will have the best performance in the dehumidification and the thermal insulation perspectives. So then we'll apply this kind of hempcrete solar chimney system to an actual project. Here is our design. We are going to design a kind of refugee camp community in Africa. Because in Africa, in the refugee camp community, the HVAC system can be hardly installed in this kind of area. So our system could provide a very comfortable indoor environment without any HVAC system. They only rely on the passive ventilations, and they will also get a very comfortable temperature and the humidity. Here we can see the robotic arms in the section drawing. The robotic arms can print the hempcrete materials in this area. And then here is the indoor rendering of our solar chimney space. And here the plan and the exterior rendering shows how that this kind of solar chimney unit to cooperate to each other. And we also include some rainwater recycling systems in this kind of a section of the solar chimneys. So that's all the introduction. Thank you.
Thank you so much. Those are great graphics, really beautiful. The next presenter is Aaron.
Okay. Can you see my screen?
Yes.
Okay, good morning. My name is Aaron Burns, and I'm a PhD student in the Engineering and Public Policy Department. My advisors are Kostas Samaras and Jeremy Mihalik. And today I'm going to talk to you about a new technology concept called smart curb space and its ability to reduce fuel consumption for surrounding vehicle traffic. So a smart curb space system is where you take a city block and the parking spaces on that city block and reserve it for delivery vehicle parking. So a delivery vehicle could place a request for parking at 10 a.m. And then they would be able to park there. It'd be reserved for them, almost like an Airbnb for delivery vehicle operations. And the problem that we're trying to address is that today, delivery vehicle operations, especially across delivery companies, are often uncoordinated. And so you may have instances of high delivery vehicle parking demand, say like 10 to 10:30 in the morning when there's many vehicles looking for parking spaces. When a delivery vehicle cannot find a parking space, it can exhibit several different behaviors. The one we focus on is double parking. Specifically, when a double parked delivery vehicle obstructs a lane of traffic, as shown in this image here. And there are a couple things going on here, but we focus on the negative impact that this lane obstruction has on vehicle congestion. And for the surrounding vehicles that might be in a queue, they are now inefficiently using fuel and wasting energy. And so what we do in this research is we look at two different perspectives. We have this status quo, uncoordinated arrival of delivery vehicles that results in double parking. And then we apply an optimization algorithm to more optimally schedule when the delivery vehicles arrive such that we can decrease double parking incidences. And then we believe that if we can reduce double parking, we should also be able to reduce congestion and therefore fuel consumption for the surrounding vehicles. So in order to test this idea, we apply an optimization algorithm called the parking slot assignment problem, which is displayed here in this graphic. And the optimization problem receives essentially a set of delivery vehicle arrivals to a set of parking spaces. But shown in red here, there are certain delivery vehicles that have to double park. They arrived and a parking space was unavailable. The optimization algorithm attempts to shift delivery vehicles such that we can accommodate some of those double parked vehicles. And so for instance, this delivery vehicle may have been able to arrive 5 minutes earlier. That was within their schedule. So by shifting them, we now can accommodate this red delivery vehicle and it no longer double parks. So the optimal scenario should have fewer total double parking events. After we have our collection of double parking events from both coordinated and uncoordinated scenarios, we can apply those through, pass them through a queuing model and determine what sort of queue we would have when we have lane obstruction. And then by understanding how many vehicles are in the queue and for what duration, we can estimate the fuel that was consumed during that queue. And what you'll see next in these results section is a comparison between the status quo and then a smart curb space optimal schedule of delivery vehicles. Let's try to scroll up here. So I'll break the results up into two sections. The first section talks about how we can reduce total minutes of double parking. I'll talk about these first two graphics here. On the left, we have 0 minutes of schedule flexibility in the delivery vehicles, and on the right, we have 15 minutes. So I could shift a car plus or minus, or a delivery vehicle plus or minus 15 minutes from when they requested they arrive. And what you can see here is that we can substantially increase the reduction in double parking minutes by almost up to 8 hours in total time if we had 4 parking spaces in our smart curb space system. Another way to look at this reduction is to think about the percent reduction in double parking we could have when we switch over to a smart curb space system. And what we'd like to see is 100% reduction in double parking minutes with smart curb space. And we do observe that here in this instance where we have 4 parking spaces and maybe 40 delivery vehicles coming to our system. We can reduce double parking by 100%. In the final section of the results here, we talk about fuel consumption. And this is one example where I had 15 minutes of flexibility and medium traffic. We estimate that a 4 parking space smart curb space system could save between 16 and 22 gallons of fuel. This would decrease if you had 3 parking spaces or 2 parking spaces. And we can extend this into a couple of key takeaways in that 16 to 22 gallons per city block per day. We could expand that to 6,000 to 8,000 gallons of fuel annually for that city block, which then could be expanded beyond just a single block to across the city to more of a regional impact, and you could expand the benefits and scale them up. And so I look forward to questions and discussions. Thank you for your time.
Thank you so much, Aaron. The next presenter is Kashkara and Nihar.
All right, can you hear me?
Yes, we can hear you and see your presentation.
All right, awesome. Good morning, everyone. I'm Kushagra Verma. I'm a PhD student in the School of Architecture. In the next 5 minutes, I will take you through a portion of an ongoing research project that I'm currently working on. The title of today's presentation is towards 4D visualization of urban building environmental performance, analysis of Manhattan's residential energy and water use performance data. The research presented here was performed on residential buildings located in the borough of Manhattan in New York City. It was also presented at the 11th International Conference on the Constructed Environment. We know, and before that, so that's me, and then my advisory committee includes Professor Erika Cochran-Hameen, Professor Kristen Kurland, Professor Peter Scupelli, and Professor Ellen Lester. For this poster, my colleague Nihar Pathak helped me with putting together all the information in an organized manner here. So we know that buildings remain one of the largest consumers of all the energy and water consumption, resulting and contributing a significant amount of greenhouse gas emissions. And unnecessarily higher energy and water consumption results in several problems, including but not limited to environmental degradation, unnecessary development of additional energy infrastructure, energy insecurity, and it also affects our community in form of higher cost burdens, especially for people of color in poor neighborhoods. The question here is, what do we do? Where do we start? How do we understand what's happening, and how can we really improve this? The performance of our buildings, existing buildings in which we have already spent a lot of energy, time, and resources. We believe that environmental benchmarking can be a solution. This research work began with the hypothesis that energy benchmarking ordinances are essential for improving the environmental performance of our existing buildings. We feel that more and more cities should pass benchmarking laws to understand the performance of their buildings and possibly improve their existing performance. Another hypothesis was that bigger and larger buildings result in higher environmental degradation. Although this is intuitive, but we wanted to show that using facts from large sample of buildings analyzed in this research. For this research, we began with analyzing New York City's energy and water performance map and the data provided through it. We reviewed local laws 84 and 133 that are the benchmarking laws in New York City. We reviewed New York City's energy and water use reports and relevant published articles. The results displayed here in this presentation are used for that. We have used descriptive and inferential statistics to identify the patterns from the large data set that was available to us. Here in the results, you can see at the top in the red is the energy use intensities. And you can see how the energy use intensity of 37 regularly benchmarked buildings representing 1.5 million square foot of floor space in New York City changed over the years from 2011 to 2017. And you can see a steep decline. You can also see that a similar pattern was observed in water use intensity and greenhouse gas emission trends. We also performed an analysis on how buildings that were built in different years and buildings of different sizes, how the energy use intensity, how the water use intensity, and how the greenhouse gas emissions, they changed over time, and what do they look like currently. It was observed in the energy use intensity analysis that buildings that were built post-war in the 1950s and through 2000, late 2000, but showed higher and should continue to show that they are really energy intense. We observed similar pattern when analyzing the water use intensity data. However, it was observed that the buildings, for some reason, and we are still investigating that the buildings that were built in 1970s are the most water intense. We also were able to show through data that the greenhouse gas emissions that come from the buildings are directly related to the building size in terms of the square footage. So you can see as the building square footage increases, the greenhouse gas emissions also directly increase. Although this is intuitive because of larger sizes of systems that are used and more resources that the building use, but this also shows us that it's the need of time to really focus on making the larger buildings and our buildings built in bigger cities more and more efficient. In conclusion and future work, you can see that our research work showed that energy use intensity, greenhouse gas emissions in residential buildings, water use intensity, all of them showed a steep decline, supporting the hypothesis that emphasizes on the need of benchmarking ordinances. However, we acknowledge and we understand that more investigation is required to look at and assess what are the other different factors that contributed to the declines the decline in energy use and water use and greenhouse gas emissions. So we have to perform further analysis and analysis of those. In this process, we were also able to identify several gaps that the future work that we will be doing are not there in the current tool that New York City uses, which is New York City's energy and water performance map. We identified that for holistic environmental assessment, it's important to include embodied carbon data and indoor environmental quality performance of the buildings in the data set as well. The embodied carbon data would help guide decision makers, the building owners, to make decisions about retrofitting or rehabilitation of the building versus demolishing the building and sending the waste to landfills. And then indoor environmental quality data to understand the effect of buildings on the building occupants. We also want to, sure. And then this is what we are really trying to do, move from 3D to 4D representation, where we want to project and show the future trends and how the buildings will perform with our recommendations for a retrofit and rehabilitation versus how they are performing now. Thank you.
Thank you so much. So our next two presentations are video presentations. So in the chat, I'm going to put the link to those. And because we numbered all the presentations ahead of time, these are presentations 14 and 16, 15 was rescinded. So that is why that number is missing. So during, after the last presentation, please feel free to look at those. So the next presentation is Shruti.
Can you see my screen?
Yes, and we can hear you.
Okay. So hello everyone. My name is Shruti, and I basically did a project on the analysis and recommendations for low carbon buildings. And the objective of my project was to analyze the passive architecture and the HVAC systems of the type of building, and to see how it affects the heating and the cooling load. And the reason why I went with the type of building was that it was built in 2017 and it was a LEED gold rated building. And for many of you who don't know what the type of building is, it is the building with the business goals in CMU. And like I said, even though it was built in 2017, it was found to be a very energy intensive building. And a little bit background about the heating HVAC systems. It uses a heat pump loop, a variable air volume system, and a variable refrigerant flow volume system for heating and cooling. And all these systems are connected to the campus's district steam heating and chilled water cooling systems. And for ventilation, there are 9 air handling units present, which provides ventilated air. And so a little bit about my analysis is in figure 2, you can see a shaded area, the D part, and that is where I perform my analysis to see what happens to the peak heating and cooling load. And all my analyses are primarily associated with the top floor, which is the 5th floor. And a little bit background about what peak heating and cooling load stands for before I go on with my analysis. And peak cooling load is the maximum amount of heat that is removed from the building by the cooling system. It generally occurs during the summer, and it is calculated by taking both the external heat gain from solar radiation and the internal heat gain from lighting, people, and equipment. And for calculating the peak heating load, you only consider the heat losses to the environment from the building. You do not consider any sort of external or internal heat gain from solar radiation or people. And now we go on to the first part of my analysis, which is about the passive architecture of the building. These are some of the changes that I'm making initially, increasing the insulation in the walls and the roofs, reducing the number of openable windows, and reducing the solar heat gain coefficient of the windows. Solar heat gain coefficient is basically just a ratio of the amount of heat that the window is letting through. And after making all of these changes, I noticed that there was approximately an 8% reduction in both the peak cooling load and the peak heating load. And if you look at figure 3, you can see that windows, lighting, and equipment sort of contribute the most to the sensible cooling load. We're only talking about sensible cooling load, not considering latent cooling load. And lighting is the most, followed by equipment. There's not much we can do about equipment in terms of how much it contributes to the cooling load. But windows, yes, we can reduce the number of windows. And the reason, and I will conclude that in the inferences as well. The next part of my analysis is about the ventilation systems. And I used an energy recovery ventilator, which is basically a form of heat exchanger with preconditions the inlet air with the exhaust air from the building. So this is obviously going to reduce the peak, the amount of energy that is going to be spent by the heating or the cooling system as shown in table 3. And table 2 shows the specifications of the chosen ERV. The next part is the heating, cooling systems and the ventilation systems. And in the TEPA building, you can see that the ventilation system is combined with the heating and the cooling system. So according to my calculations, 1,730 is the minimum amount of fresh air that is required to be brought into the building. But since the ventilation system is combined with the heating and cooling system, during the summer, approximately 8,500 CFM is being brought in, and during the winter, you have 3,300 CFM being brought in. This is a substantial increase over the minimum amount of air that is being required. And to move on to my inferences, the first, you can notice that the there is a significant reduction with each and every modification that is being performed on the baseline design. And the first thing to notice is that you can see that the peak heating load is reducing, is very sensitive to changes, but the peak cooling load isn't as much. The main reason for that is the presence of latent heat because of the ERV, the energy recovery ventilator, doesn't work well with latent heat. And the next thing, as I mentioned, is the effect of windows in terms of cooling load. So increasing the amount of daylighting the building receives also increases the amount of solar heat, and thereby the cooling system needs to work more to attain the same temperature level comfort. And hence, there needs to be a balance set between the amount of daylighting needed and the resulting cooling load. And like I said, installing ERV does not have a great effect in cooling because of the latent heat. And the last point in the inference is that separating the ventilation, heating, cooling system increases the flexibility of the various number of devices that you can use, sort of attune the thermal comfort of each occupant, reduces the peak load, and reduces the duct size of the ventilation system, which depends upon the amount of air that needs to be brought in. So these are some of my recommendations. First, separating the heating cooling system from the ventilation system, using a closed loop geothermal heating and a cooling system. This basically uses the fact that the ground stores heat during the winter and stores heat and takes heat during the summer. So again, water or air, whichever is the heat transfer media used in all the HVAC equipment, can be used to precondition. Using VRF systems, which
we're at time, Shruti.
Yeah, almost done.
Last comment.
Sorry.
Oh, I said go ahead. Last comment.
Yeah. So VRF systems are more efficient, and using them will again reduce the amount of energy that we use. And finally, installing solar panels on the available roof area is also going to reduce the carbon footprint of the building. Thank you.
Thank you so much. All right, our next presentation is Albi and Zen.
Hello, we're going to have Zen doing the slide deck today, but I will be presenting first.
All right, great. We can see your presentation.
Awesome. Can you hear me all right?
Yes, we can hear you.
All right, perfect. So hello, my name is Albi Penny. I'm a sophomore in ECE, and I'm joined by Zen today. And we're going to be talking about future data center energy efficiency and consumption, which was assigned to us through an ECE student project. So our question was, what would a large data center look like in the year 2050 from an energy use perspective? And this is a really important topic for the broader energy modeling sector as a whole, because data centers, although they currently estimated to use 1% of total electricity consumption, in the future, data centers are projected to take more and more computational demand as we shift towards more cloud computing and storage. And so there's a lot of work being done in figuring out how much energy are they going to use with current trends of energy efficiency projected into the future. And we're building on a large body of work already and trying to evaluate some current assumptions which have been made and see if they really hold up based on research from industry. So if we can talk about just what a data center is, you can go down to the model here. So a data center is composed primarily of IT equipment and infrastructure, where the IT equipment is doing the actual computations and the infrastructure is supporting that through systems such as cooling, power conditioning, and lighting. And so we are focusing on the IT equipment itself, which is shown in green. And these components are driving our model because they are expected to have the most significant impacts in energy usage in the future and have the largest changes as technology improves. While the infrastructure itself is actually leveled off in recent years. That is part of this metric called power usage efficiency or power usage effectiveness, which basically measures how much energy is used in total compared to the energy just for IT equipment. And that metric has been going towards 1 through the top data centers through Google, Amazon, Facebook, etc. And so we really focused on the main driving components of the IT equipment. And of the IT equipment, we're talking about the server, which is composed of processor and memory as our 2 main energy sinks. And through our work, we are analyzing the history on the last 10 years of energy consumption through server models. And we're going to be looking at the next 25 years through our projections. So some of the methodology, if we can go to the next section, is we're examining the energy efficiency of only computing, as mentioned before, and we are breaking up the devices into individual components and then summing their individual energy consumption to create a total model of a data center. The current model that does that is called an additive model, which has been employed in research before. And using, for example, 1 million servers in a facility, we can multiply across the individual energy consumption to get the entire facility's consumption. And so to project forward, we are using backwards looking analysis to generate trend profiles and then project those into the future up to the year 2050. And so we do that with baseline energy metrics for a constant power draw. And we also take into account the performance of the devices in the facility to get the overall computational abilities of a data center. And we use this metric, which is standard in industry, called SSJ ops, which basically evaluates what a server will be doing on a day-to-day basis. And it can benchmark across multiple different types of servers to give a standard portfolio. And we can talk about a little bit of our results, which we have just recently figured out, if you want to go talk about that, Zen.
Hi, thanks, Albie, for the introduction. Like Albie said, he's a sophomore and I'm a master's student studying electrical engineering. And so what we did with our models were we generated 2 primary results. So first of all, we looked at SSJ ops per watt, which is the benchmark metric for energy efficiency of different server lines. And so we took 3 case studies, which is first we took the most inefficient server line with the most inefficient processors, and we went up to an average processor line, and we went up to the best, most efficient processor line. And so we graphed that out for the next 25 years based on data from the last 10 years. And we saw, even conservatively, that the most inefficient line had a 4 times projected performance per watt increase. Our next result was that we took the past 10 years of energy consumption of each individual server component, and we aggregated it to form a energy consumption of a facility. And so we looked at how these server counts would increase for a given number of power draw. So inversely, we looked at the set power draw and we counted how much these servers would increase based on the last 10 years. And so if we take these 2 ideas of energy consumption within a facility increasing, and then we took the idea of energy efficiency also improving, we get a normalized plot of computational capacity in SSJ ops per second for 1 data center with a set power draw of 100 megawatts. And so in conclusion, we have that Kumi's law is expected to drastically slow down, and energy efficiency will not double every 2.6 years as claimed. And so for future work, we will expand our model to improve granularity of the components and also consider server virtualization and other types of consumption dynamics.
Thank you so much, team. And now our last presenter is Pratit.
Hello, can you see my screen?
Yes, and we can hear you very well.
Awesome. Thank you. Hello, everyone. My name is Pradit Dave, and I'm a master's student at Energy Science, Technology, and Policy. So I conducted this study under the guidance of Professor Jay Whitaker. So before starting my presentation, I would like to ask you a question. So what happens to the retired solar panels and wind turbine blades? They literally go to waste, right? They get disposed in landfills. So the same as those technologies are getting mature, this problem of recycling those like retired panels and wind turbine blades are coming into picture. This, I believe, the same will come into place once the with the higher penetration of battery storage systems, specifically for energy storage systems and for electric vehicles as well. So under this study, I'm looking at two objectives. Like first of all, I'm trying to quantify the mass of critical metals, which waste, which will be generated from the retired EV lithium-ion batteries. And I'm also looking at the second aspect of the whole ecosystem, battery manufacturing ecosystem, and look at the recycling industry and their broader landscape. So give you a quick background. Demand of as we all know that demand of lithium-ion batteries are increasing with time, and it is bound to increase even further and more exponentially with the higher penetration of like storage systems as well as electrification of transportation. One thing here to note is that the recycling rate of all these lithium-ion batteries is really poor, only with 5%. So all the, as you can see, like the also in the life cycle of the lithium-ion batteries, all the batteries are literally going to the waste after their retirement. So what I did, I tried to quantify the data of the quantified of the data of a retired EV lithium-ion batteries and the waste which will generate at the end of the year 2030 by taking the lifespan of all the automobiles as 10 years, and I've taken into consideration the EV sales till August 2021. Right. So for that data, so I calculated the average battery pack size of in a particular EV is 57 kilowatt hours, and the total number of EVs sold till August 2021 were 2.1 million in the US. So simply multiplying, then I got the rough data of 119.7 gigawatt hour of battery waste, which is which will be generated by the end of year 2030. And by this, we should keep in mind that this battery waste will be generated while the share of EVs is just 2% in the whole automobile sector, passenger vehicles sector. So here, what we actually want, what is more attractive to recyclers, is the mass of critical methods, which has the value in those like cathodes of those battery packs, right? So I calculated the masses of the metals, and they turned out to be like around 88,000 of nickel and around 15,000 metric tons of cobalt, again only from the vehicles which were sold previously. And looking at this scale, I also looked at the other side of the ecosystem, which was the startup landscape, which is kind of now shifting from pyrometallurgy to hydrometallurgy. They are coming up with more technological advancements, and supply chain is also another issue. The logistics services and like other supply chain management issues. So looking at all those aspects, I have broadly outlined some of the scope of improvements which should be emphasized in future. One of them being definitely modular battery pack design, because the glues and other layers, battery management systems and coolants, all those like all those components of battery pack make the batteries like quite difficult to disassemble. Robust policy structures which can support the recyclers, waste collection supply chains, because the batteries are literally scattered all over the place installed in the electric vehicles in the US. Lack of safety standards and for recyclers and for disassembly, lack of official database to track the data of the current amount of metals and battery packs currently used in electric vehicles, and constantly changing battery chemistries, which is quite a headache for recyclers, because that will like determine the value of recycling and extracting the metals in them. So from that, I am recommending more circular supply chain and the lithium-ion battery ecosystem. This is the line, the first horizontal line is the same linear line that I showed in background, but the extension of it starts with the diagnostics of lithium-ion battery packs at modules level and maybe at cell level as well, so that all the healthy cells maybe can be used for their, we can repurpose it and use for energy storage systems or in micromobility and other applications. In the last case, like we can definitely go with recycling, where we can recover the critical cathode materials and which can be directly again used as raw material in battery pack production. And another aspect of this circular ecosystem is design kind of a paradigm shift to design recyclable modular battery packs. And to implement all these changes, I'm recommending multifold approaches, which is giving research grants to develop such diagnostic equipments and modular battery pack designs. Second is incentives to logistics firms to make the logistics better and consumers. Third is like obviously negative reinforcements in form of regulations, and fourth is more softer kind of recommendation, which is to educate and aware all the stakeholders. So that was my presentation. Thank you very much.
Thank you very much. Thank you everyone for presenting today. Everyone did a really great job, and I'm just honestly happy to be in school with all of you. So I'm going to open the breakout rooms. We are a little bit behind schedule, as you might have seen, so I know a lot of people have to run around 12. That is fine. We'll expect to start the closing ceremonies around 11:55. So I'm going to open all the rooms right now. I'm going to share my screen really quickly, and I know some of the judges have questions, so I will get back to you in a second. So right here in the agenda, and I think I just sent it out, or I will, this was the number that you presented, and like I said, there were 2 video and 1 rescinded presentation. So if you'll just go to the room that your presentation was numbered at, so like for instance, Aaron will go to room 12, then the judges can easily find you and audience members. I will close the breakout rooms when we're all done, and we will come back. And if you're having issues getting to a breakout room, then just shoot me a message and I'm happy to put you in the breakout room you'd like to go. All right, everyone, it's 12:40, so we can get this started. So first off, thank you everybody so much for coming back. I know that we were ambitious with our timing, so everyone did an amazing job presenting, and I'm really happy to, glad to have been able to hear everybody's presentations today, and I know the judges echoed a similar statement. So again, I just want to thank the Scott Institute, Caitlin, Kristen, and Anna for helping me with this event and for all their guidance, and to all 6 of the judges who spent a lot of time going through our presentations and scoring and giving their professional expertise and opinion on this event. So without further ado, I'm going to just open the floor really quickly. I think we only have a couple judges that are still able to be here, but just to ask if any of the judges had any final comments before we give the awards. Okay. Oh, Stephen, I just saw that you unmuted.
I was just going to say a general comment of thanks, obviously, to the Scott Institute. This is a fantastic offering to keep my learning fresh on some new ideas, but then also hopefully share some wisdom and expertise and some line of questioning to help you out in future presentations. So thank you to all involved. I appreciate being a part of this.
This is Harry. I was just going to say the same thing, but the quality of the presentations was very high, so I was impressed. So thank you.
Hi, this is Purna here. I enjoyed being a part of this. 3 years ago, I was literally on the other side as a student in CMU with the STP. So thanks for having me back. I enjoyed looking at all the presentations, and they were super interesting and informative. Appreciate all the hard work everyone's put in. to make this happen. Thank you.
Thank you so much, judges. Anna, I'm going to give you the floor for a moment if you have any final thoughts.
No, thank you, Alex. I just wanted to very quickly thank the judges for spending their morning with us. Really, really thankful for your time and your expertise. Obviously, a varied set of judges this morning, and really, really appreciative. I also want to thank Alex for all of the time that she spent in coordinating all of the posters and bringing everyone together. Let's give her a virtual round of applause for an incredible event today. Thank you. Special thank you also to Caitlin and to Kristen, who were on the Scott Institute team, who were behind the scenes and making so much of this work as well. Some really, really amazing posters today. Really excited about the work that's coming out of Carnegie Mellon. We love the fact that this is all recorded. So we will have this as an asset. So you'll be able to see your snippet when we post this online. Just a reminder, we want to make sure that we have photos of the winners. So when Alex is going to announce the winners in just a minute, and when she does, we want to make sure that you all take a picture somehow creatively or whatever, but we're going to want to have something so that we can showcase your excitement. So whether you capture a moment of yourself and your team, you know, your immediate reaction, or whether you pull something together, we definitely want to have some sort of photo that we can share. So with that, Alex, thank you again. And I'm going to pass it back to you. Thanks everyone for helping us today and being a part of this.
All right, now without further ado, I'm going to announce the top 3 winners, and then I will announce the Innovation Prize winner. So in third place was Albie and Zen with Team 16, Future Data Center Energy Efficiency and Consumption. Great job. In second place was Pratit with on Team 19 with the Future of Retired Electric Vehicles, lithium-ion battery packs. Great job. And in first place is Team 13, Kushgara and Nihar, with towards 4D visualization of urban building environmental performance. Great job.
Yay. Thank you.
Fantastic job, everyone. Congratulations.
Great job. And the scores, especially for the top, I'd say like 6 or 7 places were very, very close. So great job. And then the winner of the Innovation Prize was Team 10, Sean Smiley, who I know had to drop off early. So I will, if you see him in the halls and you know him, make sure to tell him great job. So thank you everybody so much. Like Anna said, it's been a great opportunity to work on this. I know this is a frequent event, or this is like the 5th or 6th year of the CMU Energy Week poster competition. So great work. And yeah, I think that is it. So if you're a winner, we will reach out to you individually. We have your emails. And if you have have any questions or would like any information from the event, please feel free to email me or the Scott Institute, and we can give you any information you have.